To find a confidence interval for the difference in two means when we have independent samples, we start off the same way we do for any confidence interval. We have a statistic. We need to find a critical value from the distribution calculator, and we also need to know the standard deviation of our statistic. For example, using the class 1 candy data for the M&Ms, and we want to find the true difference in the amount of M&Ms for plain and peanut fun-size packs, which would be mu1 minus mu2, or we might think of this as mu plain minus mu peanut. We would start off with our statistic, which is the sample difference in those two packs. So we would do y bar plain minus y bar peanut. We estimated that, just by eyeballing it, to be the sample difference of about 9. In fact, based on our results last time, the true sample difference is 8.75 candies. So on average, we saw 8.75 candies more in the plain pack than in the peanut pack. Our critical value is going to be a t-star with some degrees of freedom. And remember, just as with the hypothesis test, those degrees of freedom are going to come from software. And we might say to ourselves, again, yay! And so we'll check and see what that looks like. The standard deviation of the statistic, as we always do with a t-test or with a t-distribution, is going to be the same as we saw for the t-test. So the standard error for y bar 1, or y bar plain, minus y bar peanut, it's going to be that same thing, which is the square root of s plain squared over n plain plus s peanut squared over n peanut. In this case, it's already worked out for us in JMP. The standard error of the difference is 0.23101. In the previous video, we worked out how we would find that by using the standard deviations of those two groups to calculate it, but having already run the test, we have the standard error calculated for us. You can show, using the standard deviations of those two groups and the sample size of 32 for those two groups, that you get the same result. Now we come back to this t-star, and let's think about those degrees of freedom. The degrees of freedom come from the software, and if we go to our output again, we see a degrees of freedom of 56.51. And again, we're not used to seeing degrees of freedom that have decimal places to them. And this is because we used the Welch-Satterthwaite approximation to calculate these degrees of freedom. So when we have degrees of freedom of something like 56.51, we are going to treat that as 56. Notice I am rounding down. We always round down our degrees of freedom because we don't want to say that we have more information than we actually do. And degrees of freedom tells us about the amount of independent pieces of information we have in calculating our statistic. So if we were to round up, we're saying that we have 57 pieces of information when really we only have 56.5. And so we'd be saying that we have more information than our calculation estimates. So we always round down, even if our inclination is to round up. So take the next lowest integer for your degrees of freedom. So we have 56 degrees of freedom, and then I'm just going to go to the distribution calculator and use it the way we always do. In this case, I want a 90% confidence interval, so I'm going to use 90% for my probability. So I go to JMP, I go to my add-ins, my teaching modules distribution calculator. I want a t-distribution with 56 degrees of freedom. I want 90% confidence, so that 90% is a probability, and I'm going to calculate my critical value. The central probability is 0.9, and I want to know how far away from the middle do I need to go to get that 90%. How far away, this 1.67, is how far away I need to go to get 90% confident, or 90% of the sample statistics or sample differences from the true mean difference. So 1.67 standard deviations should do it. So I come back here, and my t-critical value is 1.67. So I'm going to take my sample difference, 8.75, plus or minus 1.67 times my standard error, 0.231, and I get a confidence interval of 8.36 to 9.14 candies. This tells me with 90% confidence, if I only had confidence in my spelling, with 90% confidence, the true difference in the mean number of candies for plain versus peanut M&M fun size packs is contained in the interval (8.36 to 9.14). So our data are compatible with a difference no smaller than 8.36 candies up to 9.14 candies. Our data are compatible with a difference of no less than 8.36 plain candies than for peanut candies on average for M&M fun size packs. At most, our data would suggest that we would expect 9.14 more plain candies than peanut candies in M&M fun size packs. This is a pretty narrow interval, partly because we have such a large sample size as reflected in our 56 degrees of freedom. In total we had 64 candies across all the fun size packs. But also there was pretty low variability within those two groups. If we go back to our original data, or if we think about how we investigated the observations to begin with, the peanut fun size packs and the plain fun size packs were typically pretty close to their respective means. We never really saw that much variability within those groups. So even though the plain packs and the peanut packs were different from each other, a given plain pack was never that different from 7, and a peanut pack was never that different from 7 candies, and a plain pack was never that different from 16 candies. And so because we had such little variability from within groups, we have not that much difference in the not much that variability when we compare between groups. Our means are stable, and so we have good precision when we estimate the difference in the means. So we have a large effect estimated precisely, and so that gives us pretty good, pretty strong evidence of a difference and a sizable difference between these groups.